video lecture, we are going to deal with maximum minimum problems and some problems which are solved out in our textbook. The first problem is example 8, which is asking us to guess something. Okay, we are given that of all the rectangles inscribed in a circle of radius 1, so you have a circle of radius 1 and many rectangles are inscribed in the circle. We have to guess which rectangle has the largest area and the largest perimeter. So we are asked to guess the answer, right? So in the solution, we are given that we know that length and width will enter symmetrically into the formulas for area and perimeter. We know that the area of a rectangle is equal to 2 into length plus breadth, right? And no, not the area, that is the perimeter, right? Perimeter is equal to this and area is equal to length into breadth. So if we interchange length and breadth, you are going to get the same equation. That is, if we interchange length and breadth, you get 2 into b plus l, which is the same as 2 into l plus b. And similarly, if we interchange l and b, you are going to get b into l, which is the same as the area. So length and width would enter symmetrically into the formulas for area and perimeter. So that we will understand that the maximum of both area and perimeter will obviously occur when the rectangle is becoming a square. That is the possibility, because whenever we interchange breadth and length, they are appearing symmetrically in the formulas. So you get the possibility for the largest area and the largest perimeter of all the rectangles inscribed in the inside the circle of radius 1 will be a square, which is having definitely the radius, the side, that will be like this. You have a circle here and you have the square, right? So you know that the diagonals will be definitely 2, as we know that this is the center and this will be the radius and this will be internal radius. So you get the diagonals will be obviously radius plus radius, length radius plus or twice the length of radius, and that is well, the diameter, and that is the same as the diagonal of the rectangle. So here you have the length of the diagonals to be 2, and you can obtain, since this is a square, you can call it x and you can call it x and find out the length of the square, because we know that root of x square plus x square will be equal to 2, right? So you have root of 2x square is equal to 2. That will mean x root 2 is equal to 2. So you get x is equal to 2 by root 2, which is equal to root 2. So root 2 will be the length of the square we are talking about. That is not actually required in our answer, because we are just asked to guess the answer. Okay, example 9. So that is the end of example 8. Example 9, the question given is find the dimensions of a rectangular box of minimum cost. The manufacturing cost are 10 cents per square meter at the bottom, 5 cents per square meter on the sides, and 7 cents per square meter on the top. So you are given a rectangular box. Okay, so this is our rectangular box. So you're given that the cost of making this box per square meter at the bottom part, it requires 10 cents, and you're said that 5 cents per square meter are required on the sides. Sides in the sense you have 4 sides. One, this is 2, and this is on the other side, that is 4, and here you have, right, because you have one side here, the other side on the other on the opposite side, and you have side here. So you have actually 4 side. sides for the rectangle, and then you have the top. Okay. Okay, so four sides, they are given 5 cents per square meter, and for the top, it's given 7 cents are required to make the top part of the rectangular box. The volume is to be 2 cubic meters. So, volume of the rectangular box is given to be 2 meter cube. Okay, and the height is equal to 1 meter. Okay, that's all we are given. So let's see how we can solve. Okay, so basically what we need is we need a dimension of the base, L and width, because we are given the height. So what we require is we need the base, the length of the base. Okay, the length of the base and the width of the base. So these are required. So you are giving the variables L and W for the length of the base, dimension of the base, length and width of the base. And we know that the height is 1. And suppose if the total cost required to make this rectangular box is called capital C. Okay, then we know that in the question, you are given that 10 cents are required per square meter on the bottom. Okay. So, for the bottom part, if you're thinking about the bottom of the rectangular box, you have that will be definitely like we are drawing like this because we are showing that it is a 3D to give it a 3D effect. So definitely it will be of the form like this, right? So you have the length here and the W here, and this is um, the bottom part of the rectangular box, and we are given that 10 cents are required to make 1 square meter at the bottom. So you have the total area for the bottom will be LW, right? Area of the bottom part will be L into W, and we are given per square meter, so that is 10. So you have to multiply 10 with the area of the base. So what you did here is multiply 10 with area of the base. Okay, then what you did is you have 7 cents per square meter on the top. That is again the area of the top will be definitely L into W because it is a rectangular box. So area of top will be also L into W. So multiply it with 7. And then what we have to do is mm, you have 5 cents per square meter on the sides. So as we said that one part is here, right? Two parts on this side and this side. This will be these will form two sides. So they will have here the width is this and its height is given to be 1. So both of these sides will have area W into 1. So that is given here. Okay, W into 1. Okay, and you have W into 1 twice, one here and one here. So that's the 2 which is coming here. Okay, and then you have the sides coming here. Okay, this side, this one. So here you have this is the length, and this you have as the height, that is 1. So you have L into 1 for that side, and on the opposite side the same kind of sides there. So you have two types of that area, that is L into 1. So that is a 2 here, and you have taken the 2 outside the braces. From the braces you have taken it out, and then we are given that on the sides 5 cents are required to make each of the sides. So you multiply all of them with 5. So that's what which is given here, and then what you do is you just open the braces and form a simplified version of C, which is 17 LW plus 10 L plus 10 W. Okay, now we know that the volume of this rectangular box is 2, and volume of the rectangular box will be the length of the base into the width of the base into the height of the rectangular box. So that is L into W into the height, which is 1, that is equal to 2. That is a total whole length. So from this you can write W is equal to 2 divided by L. So from this part you get W is equal to 2 divided by L, and you can substitute W is equal to 2 divided by L in the equation of C. So here you have C is equal to 34 into, right here after substituting you will have this is equal to 17 into L into W will be 2 divided by L, right, plus 10 into L plus 10 into, instead of W you will have 2 divided by L, right? So when you solve for it, this L and this L will cancel because they are non-zero quantities. So you get 17 into 2, which is equal to 34 plus 10L plus 20 divided by L. So you got the cost of the rectangular, making the rectangular box in terms of one variable, just one variable, which is the length of the rectangular box. So what we have to aim is to make this cost the as minimum as possible, because that is what what the question is asking us. We have to find a minimum cost in order to make this box. So we have to minimize C. So let's call C as the function in L, because C is actually depending only on the variable L. I am calling it f of L. And we know that that is equal to 34 plus 10L plus 20 divided by L. And definitely a cost will be happening from, it will be a positive quantity, and that will vary inside the open interval 0 to infinity. Okay, since it's a positive quantity, we can say that the range is coming from 0 to infinity. Okay, then what we have to do is, uh, when L is equal to root 2, when L is equal to root 2, here uh, and basically we first saw what is f of L. Okay, f of L is equal to 34 plus 10L plus 20 divided by L. Then what you have to do is you have to find the derivative of f of L, and that will be f dash of L is equal to 10 plus 10 minus 20 divided by L square. So that's what which is written here. And then you have to find the critical points. That is the this is the method how we find the local minimum and local maximum. Okay, so when f dash of L is equal to 0, that will imply 10 minus 20 by L square is equal to 0. So you get 20 by L square is equal to 10. So that will imply L square is equal to 2. So that will be L is equal to plus or minus root 2. But we will only take L is equal to root 2 because L is always a positive quantity. So negative of minus negative root 2 is not taken into account. So you have L is equal to root 2. So that is a critical point, right? And then what you have to do is you just find the second derivative of f of L. So you get f double dash of L to be equal to 40 divided by L cube. Okay, and find the value f double dash at root 2. Okay, and you get that to be a positive quantity. Okay, so that will mean that by our various tests for local minimum and local maximum, whenever the double derivative at a critical point is strictly greater than 0, you can say that that point will be a local minimum point. And since this is the only critical point we obtained when we equated f dash of L equal to 0, it is actually not only a local minimum, it is actually the minimum in the whole domain. Or we can call it a global minimum because it is minimum of all points. Okay, thus the dimensions of the minimum cost will be when length is equal to root 2. uh, Length is equal to root 2, and you can substitute root 2 inside this f of L to find the correct cost. That is f of root 2. You calculate, you get that to be equal to 34 plus 10 root 2 plus 20 by root 2. So you get 34 root 2 plus 10 plus 20, actually plus 20 plus 20 divided by root 2, right? So you get 34 root 2 plus 40 divided by root 2, and you can solve for it. So the dimensions of the minimum cost are root 2 by root 2, okay, because we know that when L is equal to root 2, W, we had obtained that W is equal to 2 divided by root 2. So that will also be root 2. Okay. So the length and the width will be root 2, and the height is already given to be 1. So that is the specifications of our rectangular box, and this will be the minimum cost given these specifications. Okay, that is example 9, and let's see example 10. The stiffness S of a wooden beam of rectangular cross section is proportional to its breadth and the cube of its thickness. Find the stiffest rectangular beam that can be cut from a circular log of diameter d. Let's read the question once more. The stiffness S of a wooden beam of rectangular cross section. Okay, you have a rectangular cross section. Maybe think about it as yes, it is given to be a wooden, so it is a thick piece of a wooden beam, okay, and it's a cross section, and it is proportional to its breadth. Okay, the stiffness depends on the breadth, it is directly proportional to its breadth. So if uh, S is the stiffness, and if suppose breadth is denoted by B, you can say that the stiffness is directly proportional to the breadth, and the stiffness is also proportional to the cube of thickness if T is the thickness of the wooden beam. Okay, so when you have S proportional to B, you usually we denote uh, S, or if you can combine both of them to get S is proportional to BT cube. Okay, S is proportional to S is proportional to BT cube. You can combine both of them and say that. So that's what which is written in the solution. Let the breadth be B and the thickness be T. Then we can say that S is proportional to BT cube. Okay, and then you can see the figure here. So you have the cross section of the beam being cut from the log. Okay, the log is like this. Definitely you know that the log is a kind of circular shape, right? So and it is the wooden beam is being cut from the log. Okay, so that is given here, and from this, suppose you have this is the breadth and this is the thickness of the wooden beam. Then you have, if this is the center of the circle we are talking about, and this will be the radius, right? So, and you can call it d by 2, diagonal. The This will be definitely this will be t, and then you can call it d by 2, and suppose if we are giving a 0 0 as the origin of, which is the center of the circle, you can call this radius as d by 2. So we have, if this is 0, you know that this much part, okay, I'll make it more legible. If we are giving 0 0 to this the center of this circle, this much part will be definitely b by 2, right? Because this much part is b, you have this much part to be b by 2, and definitely since this much part is t, you will have this much part to be t by 2, right? So when we are thinking about the same in the coordinate geometry, you get the distance from 0 to this point will be b by 2, and the distance from this point to the point given here will be t by 2. So you have this point to be, the point given here to be b by 2 comma t by 2. Okay. So if this is the d by 2 is the radius of that circle, you can say that, and this is definitely b by 2, and this is actually 90-degree triangle. So using the Pythagorean triplets property, you can say that b by 2 the whole square plus t by 2 the whole square is equal to d by 2 the whole square. That is what which is written here. You have 1 by 2 b by 2 the whole square plus t by 2 the whole square is equal to d by 2 the whole square. And from that you can obtain the relation given there by solving it. It's very simple. Yes, you have d by 2 the whole square plus t by 2 the whole square is equal to d by 2 the whole square, and you can cut the 2 square out from everywhere, so you get b square plus t square, because all of them have common 2 square. B square plus t square is equal to d square. So b square is equal to d square minus t square. So you get b is equal to square root of d square minus t square. That is written here. And definitely this b should be coming, t should be coming inside 0 and d, because this should be a positive number that is coming inside the square root. So you have, since d minus t is strictly greater than 0, you will have t is strictly less than d, right? T is strictly less than d, and definitely t will be strictly greater than 0. So that's how you get 0 less than t less than d. Now, to maximize, so this is actually our the function you are going to talk about. So you have the function, we need the stiffness, right? This is not a function, this is one equation we get from the wooden being prepared from the circular log, okay, of diameter d, which is given. That's why, because the diameter is d, you have the radius to be d by 2. So what you have to find is, you have to find the stiffest rectangular beam. So you have to make the stiffness the maximum as possible. And as earlier we said, the stiffness S is proportional to BT cube. So you can call S to be BT cube. Okay. So call the S, which is depending on and we know that b can be written as root of d square minus t square, and d is a quantity which is given to us, so b is actually technically depending only on t, so you can change this b to root of d square minus t square. So here we had s is equal to bt cube, and which can be written as, b can be written as d square minus t square into t cube. So we are calling this s as f of t. Okay. So f of t is equal to bt cube, which is equal to um, t cube into root of d square minus t square. Then what you have to do is you have to differentiate f of t. So you get f dash of t. You know how to differentiate. When you differentiate, you get the term sitting here. You have to do it on yourself, by yourself. I'm not going to do it. So, and then you have to equate it to 0. Okay. So when you have t square into 3d square minus 4t square divided by root of d square minus t square is equal to 0. Or I think better I'll show you how to differentiate. That might be a better idea, right? We have f of t is equal to t cube into root of d square minus t square. So you know that this is a product of functions in t. So you have the first function t cube into 1 divided by 2 root d square minus t square into minus 2t, okay, plus root of d square minus t square into 3t square. So first function, this is the first function and this is the second function. You have the first function into the derivative of the second function plus the second function into the derivative of the first function. So you have this to be equal to, you can cancel them out, and you get that minus t power 4 minus t power 4 uh, plus I'm going to take the LCM, so you get t power 4 uh, plus d square minus t square. When you multiply root of d square minus t square into root of d square minus t square, you get d square minus t square into 3t square divided by root of d square minus t square. And then you get, when you simplify, you get minus t power 4 plus 3d square t square minus 3t square minus 3t square divided by root of d square minus t square. And then when you again simplify, you get that to be equal to 3d square t square minus 4t raised to 4 divided by root of d square minus t square. So that is written here. See, you have taken a t square out, right? Then what you do is equate f dash of t is equal to 0. So that will imply 3 3d square t square minus 4t raised to 4 divided by root of d square minus t square is equal to 0. So you multiply the denominator into here. So you get 3d square t square minus 4t raised to 4 is equal to 0. Okay, from that you have to find t. So you get that to be equal to t square can be taken out. So you get 3d square minus 4t square is equal to 0. And t is definitely a positive quantity, so you can cut the t square here. So you get 4t square is equal to 3d square. So t square is equal to 3d square divided by 4, that is equal to, when you get the square roots, you get d into root 3 by 4. Okay, root 3 by root 3 by 4, which is equal to d into root 3 divided by 2. Okay, so that's written here. See, root 3 into d divided by 2. So this is actually, this f dash is a critical point, and f dash has the, you have the point t which is equal to root 3 d by 2 when f dash of t is equal to 0. Since f dash of t has the same sign as 3d square minus 4t square, right? Whenever, because this t square is always a positive quantity and the denominator will also have a positive quantity. So the sign of f dash of t depends only on 3d square minus 4t square, and t is definitely smaller than d, and this will change from positive to negative at t is equal to root 3 d by 2. So that will mean, since the test for local maximum point is given there, that is, it is changing from positive to negative. So that, so here it is given that f dash of this root 3 d by 2, okay, that is positive to the left, and f dash of root 3 d by 2 is negative to the right of that point, to the right of root 3 d by 2, or to be specific, f dash of t is positive to the left and f dash of t is negative to the right of root 3d by 2. So that will mean that the function will have a maximum point at t is equal to root 3d by 2. You can solve how it becomes positive and negative by writing the lecture notes. You have to rigorously write how you obtain the positive and negative using what we had studied earlier. So the dimensions of the beam should be t is equal to root 3d by 2, and then you get b is equal to root of d square minus t square. From that you find b is equal to d by 2. So that is the dimensions at which the stiffness is becoming the maximum. Okay. Now let's see example 11. Example 11 gives us the terms marginal revenue and marginal cost were defined in section 2.1. Okay, leave it there. Prove that at the production level X naught that maximizes profit, the marginal revenue equals to the marginal cost. Okay. And determine the number of units of a commodity that should be produced to maximize the profit when the cost and revenue functions are given by cost and revenue functions are given. Okay, let's see how we can solve this problem. Okay, we have this is a formula which you have to by heart. If you are having the cost function as c of x and the revenue function as r of x, uh, the production the production p of x, okay, the function production function will be equal to the revenue function minus the cost function. Okay, so you have to keep that in mind. Don't think about the earlier portions. They are they have said that it is defined in section 2.1. Just understand that the production function p of x is equal to revenue function minus cost function at as maximum point x naught. So given prove that at a production level x naught that maximizes profit. That is at p of x naught you are having the maximum value. Okay, p of x naught is the maximum value in the given question. Okay, so at as the point x naught for p is the maximum point, we definitely at maximum point we definitely will have p dash of x naught is equal to 0. That is known to us, and that x naught is called the critical point, and we call that test as critical point test. Now, since p dash of x naught is equal to 0, definitely since p of x naught is equal to r of x naught minus c of x naught, okay, all of them are functions in x. So, definitely p dash of x naught equal to 0 will imply r dash of x naught, r dash of x naught minus c dash of x naught is equal to 0. So, that will imply r dash of x naught is equal to c dash of x naught. Okay, so that is the marginal revenue and the marginal cost. Okay, so this is called the marginal revenue. As earlier mentioned, don't panic hearing the words because they are just simple. This is marginal revenue. Marginal revenue is just the derivative of the revenue function, and marginal cost is nothing but the derivative of the cost function, marginal cost. And we said we have to show that both of them are equal, and we showed that both of them are equal. As simple as that. And the second part is determine the number of units of a commodity that should be produced to maximize the profit when the cost and revenue functions are both of them are given. Okay. And we know that the profit function is equal to revenue function minus cost function. Okay. This is what you have to keep in always in mind when such a question is given. So here also p of x is equal to r of x minus c of x. And you're given in the second part, r of x is given, subtract c of x from that. And when you simplify, you get 20x minus 0.01 x square minus 800. Okay. So we are given that x is ranging from 0 to 150. Okay. So you can write that here. The limits on x where the x is varying will be 0 to 1500. The critical points occur whenever we know p dash of x is equal to 0. So you just find p dash of x. P dash of x will be 20 minus 0.02x. right? That is equal to 0. That will mean the critical point x will be equal to, solve for this. So you have 20 is equal to 0.02x, x is equal to 20 divided by 0.02, and you will obtain x is equal to 1000. Okay. Then what you have to look is whether this critical point is a maximum point. For that, you find the double derivative of p of x. P double dash of x will be minus 0.02. That will be always a negative number. And since it is always a negative number, you know that x is equal to 1000. At x is equal to 1000. P double dash of 1000, P double dash of 1000 will also be equal to minus 0.02 because it is a constant number. So that is always strictly less than 0. So that will be a local maximum point. So then you find P of 1000. So when you get P of 1000 is equal to, you can solve putting x is equal to 1000 here. So when you simplify, you get that to be equal to 9200. And you have to check the same at the end points whether they can become, because 0 is less than or equal to x less than or equal to 1500. So usually when you check for critical points, you also check for the boundary points. So at x is equal to 0, you have uh, P of 0 is equal to minus 800. Okay. And that is a negative quantity. And we already said that P of 1000 is equal to 9200. So this cannot be taken as a maximum point. And then you have P of 1500, you calculate it. When you calculate it, that is equal to 6700, and that point, that value is also less than 9200. That is the production at 1000. Production at 1000 is greater than production at 0 and production at 1500. So 0 and 1500 cannot become maximum point. So x is equal to 1000 will be the maximum point, and the production value or the profit value will be 9200. So for solving this question, you just have to keep in mind that the profit function p of x is equal to the revenue function minus cost function. Marginal revenue is nothing but the derivative of the revenue function, and marginal cost is nothing but the derivative of the cost function. So when you write the lecture notes, you very legibly write the points which are discussed during the lecture. Now you have example 12. In this question, you are given a number a strictly greater than 0. You have to find the minimum value of a function which is equal to a plus x divided by root of ax. Okay, and you are given x is strictly greater than 0. So you give a function. You say that this value, this term is equal to a function. You give it f of x. F of x is equal to a plus x by root of x, and you are given x is strictly greater than 0, so you can say that x belongs to open interval 0 infinity. Okay, then you find the derivative of f of x. Okay, f dash of x. Okay, that will be equal to this is having u by v rule, the quotient rule. So you have v into derivative of u. So the denominator is root of ax into the derivative of the numerator. A plus x will have derivative with respect to x will be 1. Okay, minus the numerator into the derivative of the denominator divided by denominator square. Right. You have f dash of x is equal to b derivative of u minus u derivative of b divided by b square. That is what which is written here, and then you simplify to get this end result. Okay, and then you have to do is f dash of x is equal to 0. Equate the f dash of x is equal to 0, so you get a into x minus a divided by 2ax the whole raised to 3 by 2 is equal to 0, which implies a into x minus a is equal to 0, and a is a positive number. It is given, so you can just strike it off or cancel it out, so you get x is equal to a. So that is a critical point, that is only critical point in the number in the interval 0 infinity. And we can observe that f dash changes from the sign of negative to positive at x is equal to a. That is f dash of x will be negative when x is approaching from the left. So I can call it x tends to a minus, okay, and or you find some value which is less than a, and similarly f dash of x will be having showing positive value for some value x, which here x is strictly less than a, and for here you have x is strictly greater than a, and f dash will be positive. So these are two cases. So there is a swapping from negative to positive. That means it is a local minimum point, and since it is the only region we are considering, that is actually a global minimum point. And you can say that x is equal to a is a minimum point, and then you find the minimum value at a. For that, you just substitute instead of x, you can give f of a. So you get a plus a divided by root of a square, and that is equal to 2a divided by a. So you get that to be equal to 2. So 2 is the minimum value which is required in example 2. Example 12. Okay, so that is example 12. And as a remark, the result of this example, they say that we can rephrase it. Because here we know that 2 is the minimum value, right? So for every f of x, you know f of x is greater than or equal to 2 for every x belongs to 0 infinity, right? And this 2 is equal to f of 8. So instead of f of x, you can write its answer, its value a plus x divided by root of ax is greater than or equal to 2. So that is written here. And writing b instead of x, okay, you just give it a b. So you get a plus b divided by 2, that is greater than or equal to root of ab. And usually we call a plus b as the arithmetic mean of two numbers a and b, and root of ab is called the geometric mean of a and b. So this inequality is usually proved in calculus. So from this example 12, we can also end up with this remark, that is a relation between arithmetic mean of two numbers and geometric mean of two numbers. And you just cross multiply, and taking the squares, you get, or usually how it can be proved is by using this: 0 is less than or equal to root of a plus root of a minus root of b the whole square, definitely that is greater than 0, and you just simplify it. So you get a minus 2 root a ab plus b, and so that you get 2 root ab is less than or equal to a plus b, hence a plus b by 2 is greater than or equal to root of a to ab. That is how you do it in calculus. The same we obtained from example 12, we obtained the same end result. And so this is sometimes called the arithmetic geometric mean inequalities. So this is how we solve some of the examples related to maximum minimum problems. I have explained each of the steps and how to move forward while doing the problem. Some among the steps were skipped because you can do them yourself by what we have studied in the earlier classes. So please complete your notes and keep a good picture about maximum minimum problems, because they are very important and they can come for any in any part of the university examination. So be very vigilant about studying these portions. So thank you for watching out this lecture, and see you in the next video lecture, which is related to mean value theorem. Thank you.